Welcome to Lesson 34, Validation of Aseptic Processes. In this lesson, we're going to be looking at the preparation and filtration of solutions, aseptic processes, barrier technology, sterilization of media and buffers, filter validation, and media fills. There are two categories of sterile products, as we've mentioned in our overview section. Those that we can sterilize in the final container, so terminally sterilized, and those that cannot be terminally sterilized. So they must be aseptically prepared, and where there's because we might have proteins that would denature from heat, and that's what this lesson is dealing with. So aseptic processing, the objective is to maintain the sterility of a product that is assembled from sterile components. You have to operate in conditions so as to prevent microbial contamination at all times. The preparation and filtration of solutions. Solutions to be sterile filtered prepared in a grade C environment. If they are not to be filtered, preparation should be prepared in a grade A environment with a grade B background, so that might be for things like ointments, creams, suspensions and emulsions. Prepared solutions are filtered through a sterile membrane of 0.22 micrometers or less. The membrane filter into a previously sterilized container. The filters remove bacteria and molds. It doesn't remove all viruses or microplasmas. Filtration should be carried out under positive pressure to prevent any dust, dirt or contamination from entering the room. Consideration should be given to complementing filtration processes with some form of heat treatment if possible. And that might be for your filters, for your glass, for other aspects of the process if your product cannot be sterilized using heat treatment. Double filter or a second filter at the point of fill is advisable. Filters should not shed any particles, and asbestos-containing filters should not be used. The same filter should not be used for more than 1 day unless you have validated it as such. If the bulk product is stored in sealed vessels, pressure release outlets have to have a hydrophobic microbial retentive air filter to prevent any contamination from reaching the product. Time limits should be established for each phase of the processing. So for example, the maximum period between the start of your bulk product compounding and your sterilization, in this case your filtration. The maximum permitted holding time of the bulk if it's held after filtration prior to filling. The product exposure on the processing line would be a critical time to have a hold time established. Storage of sterilized containers and components prior to being used. The total time for your product filtration to prevent organisms from penetrating the filter. And the maximum time for upstream filters that are used for clarification or particle removal that can support microbial attachment. So that needs to be defined. Example of an aseptic process. Your API is provided as a powder in a drum. The API then is formulated by dissolving it in a liquid to the correct concentration. The liquid product is sterilely filtered in an aseptic environment. The filtered liquid is filled into vials and dried if appropriate or sealed. Finish step. The great risk to the product is between filtration and stoppering, so that part of the process is very critical. The process obviously needs to be completed in an aseptic environment so that no microbial contamination can occur. Aseptic processing. So first of all, we're looking at the manufacturing environment. And in that we have our barrier technology, which we will be talking about in a minute. We also look at our clean rooms as part of that, and then training for personnel and the behaviour of personnel in an aseptic environment. Cleaning is obviously vitally important for aseptic processing. Your clean in place needs to be very effectively done, and your clean out of place also. The third part is your sterilization. So your sterilization can happen in a number of different ways, with your steam in place, your steam out of place using an autoclave, via filtration or via pyrogenation. Closed fill systems then, so your media fills, which we will be talking about in a couple of minutes. Aseptic vial filling. We need to talk about cleaning, sterilization, the filtration aspect of it, how it's filled, and then it's capped. Barrier isolation technology. Barrier isolation technology is the restriction of personnel movement for protecting the product from contact with personnel and also from the environment. Examples include restricted access barrier system. So that's clean room environments is another example where aseptic processing occurs. Laminar airflow hoods, LAFs, isolators, which are glove boxes, biological safety cabinets, barrier suits, your clean room garbing. All of these are methods to have barrier isolation technology in place. Your laminar airflows, your isolators are your glove boxes, and they look something like this. Your barrier suits, so your garbing inside in your clean rooms, so they look something like this. And then your clean rooms themselves, the RABS. Facilities, general clean room design. So as part of a general cleanroom design, you will see two links. The first one is your material access link called the MAL, and the second one is the PAL, the personnel access link. And you can see there's double doors here. There's also a step over bench. There will be pressure differentials between the rooms also. There would be very strict control as to what level of garbing needs to be done at each stage of entry into a clean room. Glove boxes and full suites might look something like this. And half suits and isolators would look something like this. So there's quite a huge effort put into making sure that the products being manufactured are sterile. Filtration. This is an example of liquid media and gas sterilization in a biopharma. It is necessary to treat the liquid media and the gases in order to remove all the microorganisms present. So you can see here the aeration, the gas, whether it's air or whatever is coming in, it's filtered and it's sterilizing grade filter here before it goes into your bioreactor for your aeration. And your media similarly is pre-filtered and sterilizing grade filtered before it goes through here. Also your exhaust air coming out is also filtered. The filtration process. So this is a typical filtration process. So you could have a pre-filter, you could have a particle filter, a final filter, and then finally a sterile filter as part of your process. Sterilizing media and buffers. So you've got your incoming material with a positive displacement pump, your filtration system then, and your holding tank going outwards. What we're interested in is the qualification activities that need to occur for each of these aspects of the process. So you have your sterilization and your filter qualification as part of your filtration process, and in terms of your holding tank you would be looking to qualify your clean in place, your steam in place, and your tank vessel hold times. They would be all components of your qualification of your system. Inline sterilizing filters. A sterilizing filter is one that can retain 10 to the 7 CFUs, so that's brevondomonas diminuta per centimetre squared of the filter surface area. A filter with 0.2 micrometer pore size rating is typically used as a sterilizing grade filter. It's often discarded after each batch. Redundancy is also often built into the process design. They are steam sterilized. There's rigorous design specifications must be prepared for inline filters to ensure that they are fit for purpose. The user can accept validation claims from the filter manufacturer. However, the responsibility for validation remains with the user regardless. The PQ stage and ultimately process validation confirms that the correct filter was selected. Parameters that must be considered during the design or selection of the appropriate product. The process flow rate, the throughput, the sterilizability, the organism and the product retention, any extractable levels, particle shedding, product stability, compatibility, toxicity, non-pyrogenicity, thermal and pressure tolerance. All of these aspects would be part of your design specification and they would be reviewed during your DQ. Your IQ then will verify that the vendor has supplied the filter to these relevant specs. Filter qualification PQ tests. So the first thing you want to check is your filter integrity. This detects any leaks or perforations in your filter. The filter integrity should be verified before and after filtration. And the way we do that is either through a bubble point test, which we will talk about in a minute, the pressure hold, seeing if you can hold the pressure, and forward flow. It's a non-destructive test. The second type is a bacterial challenge test. This is a destructive test, and the validation must include microbiological challenges that simulate the worst case production conditions. The product is used as a carrier unless it's otherwise justified. We have to prove the bubble point test. So when air or nitrogen are put through the filter under regulated pressure, if we see displacement of bubbles, we can measure the displacement that might bring, and that will give us a determination of any damage to the filter. The bubble point test detects any filter leaks or perforations that might have occurred during the filtration. And we've got our calculation for it up here. Media fills. 21 CFR Part 211113 details that media fills must be adequately validated to ensure the sterility of the products. Media fills. It's an aseptic process that must be validated using a microbiological growth medium in place of the product. This is known as a media fill or process simulation. So our first thing to do is select an appropriate growth medium. Then we run through the process using a growth medium in place of the product. The sealed containers with the medium are then incubated and to detect any microbial contamination. Microbial growth indicates that we have been operating under non-aseptic conditions in the process, so that's not a result that we want to happen. Media fills. The FDA recommends that media fill program addresses issues such as human factors that could cause contamination, so how humans behave in the clean room, things like operator fatigue. The media fill should be representative of the normal level of intervention during the process run, so you want to simulate the process as closely as you possibly can with your media fill. Aseptic assembly of equipment, so startup is one of the riskiest times for contamination, so that would need to be part of your media fill. The number of personnel and their activities as per normal production should be the same during a media fill as a normal process run. So normal shift changes, breaks and gown changes should occur during a media fill, and normal aseptic sample collections as well. At least 3 consecutive runs of a media fill is needed to prove that your process is aseptic. Media fills are generally run routinely on a semi-annual basis as part of the revalidation of your aseptic processing. All personnel who are authorised to enter aseptic processing rooms during the manufacture will be monitored at least once a year. Participation is consistent with the amount of duties that somebody would have in the clean room. This is a typical aseptic vial filling process. So your product is aseptically filled into your vial. Step 2, the stopper is partially inserted and the vial is placed in a lyophilizer. Step 3, when that is complete, the stopper is sealed. An aluminium cap is placed then on your vial and that is crimped onto the neck of the bottle. So in a typical aseptic process, you've got your glassware coming in that has been sterilised, your stoppers have been prepared and sterilised, your product is coming in and it's prepared and sterilised, your aseptic filling occurs. If it needs to be lyophilized, it is, or if it's left in a liquid form, that's the same case. Then the product is capped, caps have been prepared, and then the product is stored. So as part of that entire process, we have a number of things that we need to consider for validation activities. The first one is your cleaning processes, your sterilisation processes, your filtration processes, the actual filling of the product, your media fill runs, and validation of your clean room in addition. There's quite a large number of validation activities to occur. Aseptic vial filling in a real facility might look something like this. References and further reading for you. So these will be listed in the appendix to your lesson plan. Have a read through them and have a look at them. Over to you. Can you explain what is involved in the aseptic process? What is barrier technology? How would you go about validating a filter? Thank you very much for your time and attention.